So good morning, welcome to lecture 38 of thermodynamics of materials. Okay. Now another point is, so we are actually going to take up finishing part, that is adiabatic. To find delta S for the adiabatic, because other threes are over for the adiabatic process. Adiabatic. Okay. This is okay, and remember what is the relationship. Okay, you have noted this though. Can you remove this? Remove this. Process. Remember what was the relationship I got last year? Recall general relation. Delta is recall general relation. General relation quickly. Delta S is what? NCB ln T2 by, recall last year I gave you this, plus R ln V2 by V1. Just recall reference, okay? This was already done. So accordingly I covered what? Isothermal. Out. Answer R ln V2 by V1. Oh, NR ln V2 by V1. Constant volume. NCBln T2 by T1. Constant pressure. You add this NCPLN T2 by T1, discussed last class. Okay. So this is actually for N moles. N moles of ideal gas as system. As system. Recall? So delta S for isothermal, constant pressure, constant volume, and constant pressure process. Pressure process is already discussed. Already discussed in the last class. So you don't have any difficulty to follow the continuity. So adiabatic remains. Start. Adiabatic what? I again start with this. So start. First is adiabatic is very difficult. I always say slippery. Okay. Deceptive. So first is go slowly. First is a reversible adiabatic and irreversible. Reversible adiabatic and irreversible adiabatic. Recall this. Don't worry. I don't want to say anything. Let us not waste time. Quickly again write it back here. Helps you. You know the answer. What is delta S? This delta S means delta S system. Remember, this delta S is the remember always delta S system. This is delta S process. It's a process system. Same thing. System are not going the process. S2 minus S1. S2 is the entropy of the system at state 2. So delta S system. Okay? This we don't write, but this is implied. Delta S, delta H, delta U. A process also. What is this? The same thing. Delta system. Delta S is what? N. What's the answer? Tell me. I'm writing. What should be the answer? Expected answer? Delta S system for reversible adiabatic. What is the expectation? Delta S for adiabatic, reversible adiabatic? 0. Adiabatic process. No way. No way. No way. Delta S system is 0. How much heat is absorbed? Q reversible. Adiabatic means no heat is. Okay, that is already discussed. One by one is 0. Remember this. Delta system is 0. Okay. We actually found delta S in reverse also. So remember, for this 0 should be 0. So you should be prepared for this. So this. Okay. Good boy. NCB ln T2 by T1 is what? NCB ln T2 by T1 is what? Okay. Oh, recall. TB to the by gamma, T1, V1 power gamma minus 1 is T2 V2 to the power gamma minus 1 reversible adiabatic. This relation apply this T2 by T1 is what? Tell me, let me write here. T2 by T1 is V1 by V2 power gamma minus 1. Are you all set? See, T1 by T2 by T1 is V1. Is okay, no problem. Plus NR ln V2 by V1. Go fast. Is what? Gamma minus 1 is what? Gamma minus 1 is, right here, gamma minus 1 is Cp by Cb minus 1 is Cp minus Cb by Cb, R by Cb, R divided by Cb. So take this power, log power, oh, ln is here. Ah, you don't notice this. ln is here. ln is here. So gamma minus 1 is what? R by Cb. If you take this R by Cb here, what it is? Resulting R by Cb times Cb is R, NR ln V1 by V2 plus NR ln V2 by V1. V1 by V2 is inverse of V2 by V1, means negative. One is log is negative. So mutually negative means this is 0, as expected. Is clear with you? Huh? Clear? Yes. What is this? This is log V1 by V2. This is log V2 by V1. If you add this, what you will get? Log 1 is 0. Okay? Always log x is minus log 1 by x. Remember this. This is minus. This you should know. Okay? Reversible, irreversible. Quickly. Now this is something. Come on. Irreversible adiabatic. I have already announced the test date. Okay. I will remove this. It was written there. This 15th. Remember, 15th, 11 to 12, 15th of Thursday, 1 week. So irreversible adiabatic. This is actually assignment 4 problem. Okay. This is also assignment 4 problem. I'm solving here. At the same time, it is shown here, and also this will cover the assignment. Okay, follow this. Irreversible, or you write, or for any process. Any process. This is interesting. Not only irreversible adiabatic, but or for any process. Okay. But start. What is the rule? Okay. Okay. Delta S is what? Let me write N Cb ln T2 by T1 plus NR ln V2 by P1. Do you have no objection? First line, no objection. What is this? N Cb ln, what is T2? P2 V2 by P1 V1. Okay, what is this? Keep on writing. Achha, N Cb, please follow. I am writing in one step. Cb plus R. R I am taking this side, and ln V2 by V1 I am retaining this side. And then what remains? Other things are N Cb ln P2 by P1. Take a look. P2 by P1. Good boy. NCP. This is NCP. NCP ln V2 by V1 plus NCB ln P2 by P1. Okay. Now what I am doing, first of all I tell you, this is applied for how many moles of the system? N moles. So I am giving, for this particular problem, I am giving it delta S N, so extensive prime. Okay. So for N moles of the system. This time I am doing this because I will make it actually 1 mole later. For N moles of the system, I will make it 1 mole later. So what is this? N mole system and extensive property. You always note this. Extensive property. Now I divide by NCB. Okay, follow this. Or delta S prime Coming. NCB, follow, please follow. NCB is what? Gamma. Do you have any difficulty? This line? NCB dividing through by NCB. So CP by CB is gamma. NN cancel, and this all gone, okay? Or note, or delta S by CB, write this, is what? What I read? ln V2 by V1 power gamma, powered, plus ln P2 by P1. No difficulty. No difficulty. Why? What is delta S? Now tell me, what is delta S? Yes, molar. This is total for n mole. This is a total property, total entropy change. That is right. This is total heat capacity, molar heat capacity. For n moles, total 1 mole molar. Total delta S. Total, okay. Total, what is this? For n moles of the system, total entropy change of the system. And what is this? Delta S, guess? Molar for 1 mole system. So this is what? Delta S is what? Delta S prime by n. This is extensive, intensive. So this is molar entropy change. Entropy change. Guess this, okay? Again, right? You know this extensive, intensive. So this is right. This is extensive. This is intensive. Recall that rule. This is n also. Extensive. Recall this. Okay. So all set. So I am start this place and go up. Go up there. Maybe this side, huh? This side. Let us not disturb this. Take up here. What you are getting? ln or delta S by CB is what? ln. I am writing something, you follow. P2, V2 to the power gamma by P1, V1 power gamma. Please check this. Check right hand side. ln, sum is product. And it's okay, fantastic. Or P2, V2 to the power gamma by P1, V1 to the power gamma is, is there any? It's okay, let it be. So is delta S by e to the power delta S by CB. Or I am writing something in follow last line perhaps. P1 to the gamma is e to the power minus delta S by CB. P2 V2 to the power gamma. You all set? This is something. This is I already told you once. For irreversible adiabatic, what is the relation? If is not, this is true. So this is derived today. This is assignment problem also today. Assignment 4. This is number 3 perhaps. So this is covered also. This is not only for note this. This is not only for irreversible adiabatic. But okay, irreversible adiabatic is very important. But for any process, any dam. This is general relationship. So okay. So this is see, looks like P1 V1 power gamma is P2 V2 power gamma, which is good for reversible adiabatic. So quickly check for, okay. So this is general relationship, right? General, not only general relation. Is it good for? Yes. So for reversible adiabatic, what is the delta S? Delta S 0. If I have to put that back into this, for reverse is delta S 0. What you are getting? This leads to what? It is 0 means 1. So P1 V1 power gamma is P2 V2. Reconciled, which you know. So you are very happy. This part is over. This was pending. This is over. Last time we didn't get time. So this part is over. So all delta is for all ideal 4 ideal processes with n moles of ideal gas system is all over. Okay, and for adiabatic, reversible and irreversible both separately addressed because this is different, because here final state are affected. So you don't say that these are same value. Don't say this because the initial state may be same, but the final state always change because of the property that path affects the state, final state. So you all set. So think about this, remove this, this part is over. So now take up the assignment quickly. Now take up the assignment. Assignment number 4. Is it due today, remember? Huh? You're not sure? It's due today. So let us solve this with 2 important problems, a couple of simple problems, okay? Very good. Refer to problem 1. Problem 1 is what? Has anyone solved the problem 1? Any of you? Huh? Didn't get time? Didn't get time. Problem 1 of assignment number 2. What is this? Refer to problem 1 of assignment number 2. What is the problem? Recall. What is the problem? Assignment 2, first problem was what? What was this? Find delta S cycle. This is the problem. Okay. So what is that cycle? Recall. Problem. Okay. You have given the class test. So you should have been prepared. What is the first problem for assignment 2? A cycle was given. Assignment 2, first problem. A cycle was given. There you found 4 things. Already 4 things. Q, H, delta U, delta U, delta H, Q, W. 4 things as usual. Today another thing, delta S. So cycle is what? What is the cycle? The given cycle is solution. Quickly and very easy actually. The given cycle is, recall, cycle is, recall. Because recall means why? It is already referring. Okay. What is that? This is the cycle. PV diagram. Remember this. Because this, the constant pressure, constant volume. 1, 2, 3, 4. So this is the cycle. You think about the answer. What is the answer? Answer, tell me, what is the answer? Huh? Give me the answer. Answer. What is the answer? You don't have the answer. Delta cycle, okay, you give one test and then you forget everything. Okay. How much it will be the answer? Entropy is state property. So you have to show that it is 0 this time. I also found delta U cycle is 0, delta H cycle is 0, but Q cycle is not 0, W cycle is not 0. Remember today this, just complete this. Since you don't remember, I don't remember too. This was 600 Kelvin. This was 1220 Kelvin. 1, 2, I'm very sorry. This doesn't go this way. Okay, somehow I made a mistake. This is 2. Oh, sorry. 2, 3, 4. So this is 2 is what? 305 Kelvin. This is again 610 Kelvin. This is again 12. This is the cycle. First check this. Cycle is 1, 2, 3, 4, 1. Name the cycle of the path. This is a cycle. What is this one? 1220. What are the pressures? Like 10.5 atmosphere. 10.5 atmosphere. B also given. So everything is given 5 and this is 10 and liter. Hello, hey, don't. Okay. Marmar. Okay. This. Okay, so delta is start. What is a step by step? Delta is 1 to 2. What is this? What process it is? Delta is 1 to 2. See, you neither solve this, you are not following this. Hey, what are you doing? Okay, see, I am talking here. Then you score 0. Oh, what will be? Okay, sir, will you please take another class? Very bad. Bad habit. See, you are sitting here, you are attending class means actually you are not giving any examination now, which is coming next period. So follow this at least. You have not come prepared with your answers and you are not following this and then participating. Easy thing I am asking. Constant follow, we are not participating. See, this is actually, if you follow this class, you will have preparation 60% over, at least 50% over. Yeah. Then you go back and then you couldn't manage this, then you will not nervous. The moment nervous, simple things you will not follow. You don't understand what is H. A right expression for delta H. Randomly writing all nonsenses. No, because mentally disturbed, he knows, they know very well that they don't know the things. They are only asking friends, hey, how much you have taken preparation? Hey, how much you have taken preparation? Have you read this? Have you read? These are doing and wasting time. And when in the examination with proper invigilation, strict invigilation, total nervous, because there is no kind of exchange. Help. Total nervous. Cannot distinguish between H and delta H after so many classes. And DH. What should I say? This happens because you are not taking attention, okay, proper time. Now, once you actually know these things go out of your control, you will be nervous. And nervous means brain will not work. Nervous, it will happen to me also. It will happen to me also, don't worry. To everyone. Preparation. Preparation is a great issue. Strong. I have come here, you think actually empty-handed. I'm taking these easy things, I'm taking preparation. This easy thing. Still I'm saying, okay, what is this? Study meaning say. And then I am very confident. I'm giving you this. If any question comes, I will answer. Confidence. Then I will always actually humble. This happens. To teacher, to student, anyone. Preparations. Strong. What happens? Then they will not actually move around this place to that place. Your examination is the next period or 2 periods later. Or you are actually not thinking about their talking. He is continuously talking and he is also continuously talking, exchanging everything. So you cannot answer these questions. Thus, it is good I should only write the answers and jot down and go back. And what will happen? The same thing will happen. 3 students pass up, 4 students pass. Below 40%, above 40%, perhaps 4 students if I remember well. This will happen. 5 students, maybe 5 students. 13, 14, 15 and 21, 21. 5 students out of 32. This is pass mark. Their pass mark. So this will happen. This is only first classes. The second class is supposedly more complicated topics are there, more difficult. And when it comes to semester, you know what you will do. You will give up hope. But you are better students here who have come here. But most students have not come. They are taking preparation for the next test. And you are losing this. Then when you manage, you will lose that test. And that subject again. Because when this examination will come, then they will not take preparation. So you will understand. Total actually mixed up. So take in proper help. Delta is 1 to 2 is what? What type of process it is? What type of process? Constant volume is NCBL and you don't have to. So dq reversible, I am showing once. dq reversible by T, the integration from 1 to 2. What is dq reversible in a constant volume process? NCB dt. NCB dt. NCB dt. Constant volumes dq. dq is constant. CB definition follow. CB is dq by dt at constant. First line, not second line. First line. dq. Heat capacity means heat first. Enthalpy later. We'll see that. NCB dt. Okay, good boy. What is this? NCB dt is what? How much? Tell me. NCB outside ln T2 by T1. Oh, what is that value? Oh, T2 by T1, right? T2 by T1. Oh, T2 is how much? 305 by 610. Okay, what is this? Sorry, you write that. So it is half. Can I write NCB ln2? You don't mind, na? Ln half is minus ln2. Minus ln2. Delta is 1 to 2. Delta is 2 to 3 is what? It's a constant pressure, as you see. So similarly again, I am writing once more for you. 2 to 3 is a constant pressure, right? Right, constant volume process, right? Constant. I'm trying utmost to clarify. Constant volume process, constant volume step, constant. Okay, happy? Constant volume. Then this constant pressure step. What is the DQ? Fast thing. DQ is then you have to ask what is DH. You have to write it. That's too cool. What is DH? Then you will answer. Get back. DQ is DH under constant pressure, no doubt. But DH, how DH will get the result from where? Why did you get? You come back to DQ. Take a resort to DQ. Because DQ is by definition. CP is Dale to fast line you follow. DQ. And moreover, see, I tell you something about DQ when I ask, or you ask yourself. See, there are two ways. One is direct, it comes directly from the definition of CP, CB1. That is NCB DT, NCB DT. This one. But in another case, there is no DQ. There is no, but I am very sorry, there is no change in temperature. How will you get the DQ? Say NCP DT or NCB DT. For some process, you cannot apply this because DT is 0. But DQ is there. DQ means isothermal process. Namely isothermal. What you will do? I will check this way you prepare. Oh, these cases DQ is this, oh, fast DQ, then DH. This way I do. You want to know an example? I do myself. This way I am here. Oh, no, fasting is what? DQ. But then yesterday I thought about this, okay? How to remove confusion from you. Randomly don't know. Randomly what okay, say DQ is DH. Yes, actually, ready in his mind. So DQ. How? What's the answer? This answer is required. DH is there. Then what shall I do? Another. So DT. If isothermal, will you write this? That is particularly constant volume. It is already constant volume, so that's why you write. Isothermal you will not write, but what you write, then you ask yourself, how to manage DQ for isothermal? Then you say, well, Baba, first law. DQ is du plus dw. dw will never fail you. dw is always available. P external dv, P dv, etc., etc., etc. du is also very easy for isothermal process. For 0. So DQ is essentially dw, and dw is always, that never fails. That I don't know, dw is dw, okay, PdV. PdV, okay, so PdV and then the integration you can do always, okay, see, okay. So this is how, yesterday only I thought actually how to clarify these things to students. Jump, sometimes this randomly will not do. So DQ, DH, number of times you are saying DQ is DH, I've seen. Okay, but does it help solve the problem? So, what shall I write here? You write is it fully right? Because it is under constant pressure. 2 to 3. I am also teaching you how to prepare for this subject. Not only this semester, what life is more important, more durable, and okay, more actually I say more extensive. Life is different, okay, different, you know. So what I say you got the pass mark, barely pass mark, no problem. You can be a giant in thermodynamics, I can tell you. Giant. Constant pressure, what shall I write this time? NCP dt by T, right? Constant pressure. Constant P process. Happy? So what it is? 2 to 3 NCP ln. I should write 2 to 3. Okay, I am writing here. NCP ln T3 by T2. What are they? NCP T3 is what you see? 610 by 305. So NCP ln2. Delta S. Delta is 3 to 1. Similarly, I am writing similarly. Similarly, don't take time for this easy thing. Is what? 3 to 1, tell me. Similarly, again constant volume. NCB ln, I am writing. NCB, follow. NCB ln. Final is 1220 over 610 is NCB ln2. And delta S for 3 to 4. Hello. 1 to 2, 2 to 3, 3 to 4. 4 to last is 4 to 1. Last step is what? Again, 4 to 1 is what? Constant pressure. What is the answer? Yes, Nirjal, what is the answer? 4 to 1? Ln? Oh. Ln, 3 to 4 to 1, ln T1 by T4. What is this? Because unnecessary, na? Let me write the T1 final. Final is what? 610 by 1220. Good boy. So minus NCP ln 2. Happy? So combine this. 0 to. Hence delta S 1 to 2. Delta cycle. Delta S cycle is delta S 1 to 2 plus delta S 2 to 3 plus delta S 3 to 4, delta S 4 to 1 is what? You write LCB ln 2, okay, you get this is 0. As expected. I can write as expected. As a for a state property. Expected of a state property like entropy in a cyclic process. In a cyclic process. Write this. Okay? I may not write. Over. One problem over. Down. So next is problem 2. So remove this. Problem 2. Problem 2. Just. Problem 2 is easy, short, very short problem. Oh, problem just now discussed. Problem 2 follow what is given. Okay. So that for the change, let me write. So that for the change of state, change of state 1 to 2, oh, one to 2. For n moles of an ideal gas, P1 V1 power gamma times e to the power minus S1 by CV is P2 V2 to the power gamma e to the power minus S2 by, okay. So I am writing solved today. Already solved today. Already solved today. So problem 2 is over. So remove all these things. Problem 3 is also a short problem. I am solving, writing here. Problem 3. Problem 3. That's problem 3 I am writing here. Remove this. Any difficulty? Problem 3. Happy? Del S find del S del P at constant temperature for 1 moles of an ideal gas. Question? Okay, answers also I gave. So it was easy for you to solve at least first 3 problems. First 2, second problem may not be. First 1 and 2, only 2 problems you could solve yourself. Okay. Achha, what is this S1? Let us say Nirjot. What is the S1? S1 is what? Just S1, let me know. Entropy of? State 1. Achha. State 1. So system. System is n moles of ideal gas. For how many moles? Molars. 1 mole. Moles may be n because you have already divided. Is reduced to molar, no? Remember, this one is molar. If you make it to n moles, then it should be NCB. Remember. So it is molar and molar matching. Careful. So molar entropy. N moles may be there, but 1 mole contribution we are considering in this expression. Okay. If you say, if you must and n moles are you interested? Okay. S1 prime, and you will get a n Cb is also molar. For any moles, you should consider NCb. S1 prime by NCb. A moment ago I said, sorry, S1 by N is S1. Okay. So how to solve this problem? Okay. Solution I am doing here. Two ways. Okay. First method. Solution. I am solving here. First method is, I'll tell you today or tomorrow, not today, next class, soon, del S by del P, it will be proved. Soon. What I'll prove? Delta S by delta PT. I told you perhaps. Del V, del T at constant pressure. This is okay. This will be put. This is called Maxwell relation. Maxwell relation. Letter means in one line. This will syllabus here. Maxwell relation. I will prove everything. Okay, this I'll address. This also I told you other day. Yesterday I gave you a note. Gave some equation. What is this? What is this? What is alpha? Noting alpha is del B del T at constant pressure. What is the name of this? Expansivity. Volume temperature expansion. How much expands? Coefficient of expansion. Coefficient of volume expansion. Expansivity. Expansion coefficient. So many names. So, and 1 by B. Okay? Like linear expansion, then surface, then volume. This is expansion, isobaric expansivity. Okay. Once more writing, isobaric because constant pressure. Isobaric expansivity means coefficient of expansion. In short, expansivity. Coefficient of expansion or coefficient of expansion. Coefficient of expansion. Expansion. This I told you. For the last problem also this is needed. What it becomes then? Minus. In additional writing. This gives you what? If it is true, then this gives you what? What is this? Minus alpha B. Have I not given you this relationship in the last class? You require to use the del S by del P. And okay, what is this? Del S by del P and del H by del P. Del H by del P already I gave. Thermochemistry, how is the effect of pressure on enthalpy at a given temperature? And what is the meaning of this? How pressure changes the entropy. How entropy is changed by application of pressure. Easy thing. Don't go by mathematical relation. Give physically what means. And under constant isothermal condition. It is as good as this. This is expansivity. Means close to it, related to it, and is minus. So I am telling you what? You know what is the value of alpha for ideal gas? One more. For ideal gas, alpha is what? 1 by T. If you put 1 by T, minus V by T is the answer. Minus V by T is what? Minus V by T. Okay? For ideal gas, alpha, good. You know how can you prove alpha is 1 by T? Use this ideal gas equation here. Okay, good boy. So it is minus V by T. Alpha is 1 by T for ideal gas. Right? For ideal gas. You can do yourself. You can do you take V is RT by P. I am giving you V is RT by P ddt of this. R by PV. R by PV. PV is RT. R by RT. 1 by T. Easy, quick. Very good. And V by T is what? This is the answer. But have I given the answer? Answer I give is as good as minus R by P. Answer. V by T, it is better. With one pressure only get. Del S by del P is minus R. What does it mean? If we increase the pressure, this will decrease means increase actually. Entropy will increase with increase in pressure. Pressure increasing means this side is decreasing and negative decreasing means increasing. So if we give pressure to this, entropy will increase. Pressure to anything, okay? Entropy will increase. Gold is the example. So pressurize it. Okay? Similarly enthalpy. But note one thing, this effect are very small. Here. Alpha B. This effect is why I said this is small I am saying. Effect is there, but small effect. Why? Effect of pressure on entropy is small. From this can you tell me? Anyone? I said this. Molar volume is small for solid and liquid. Okay, not for gas. Real gas idea. The molar volume for solid liquid very small. What example I give always? What example? Molar volume is very small compared to solid liquid. compared to gas. What example I often give? Molar volume of solid liquid is very small. Easy example I always take. To convince you and convince you and convince you. So you don't know, oh, molar volume, blindly. No feeling. Feeling inside, feeling. Molar volume, 1 mole volume. What example? Water is a liquid. What is the 1 mole volume? What is water of 1 mole? 18 cc. 1 mole means 18 gram and density is 18 cc compared to 1 mole of any gas, ideal gas at NTP, STP, 22.4 liters. So molar volume is large compared to this. This is small compared to this, negligible. So if it is small for solid liquid, solid is meaningless. Small effect. This I told, del H by del P at constant temperature, small effect. This is also considered in the last problem. Effect of pressure on enthalpy, effect of pressure on entropy. For solids, gold solid, this example. So this is okay, but very good, but okay, alternative. Suppose you don't know Maxwell, sir. I don't know to Maxwell. Just Maxwell, I don't know. Then alternatively, let us try alternatively. Second method. How to do del S by del P at constant temperature is what? Can you tell me, give me this, okay? Under constant pressure, under constant temperature means effect, you are changing pressure on a system without changing the temperature, isothermal condition. Impossible. And how the interpretation is. Okay, the ideal gas is the system. What is the, I'm writing? dq is ds is, sorry, ds is what? dq reversible, follow this, follow with me, interesting. So alternative I'm doing. ds is dq reversible, this is that. What is dq reversible? This is which process? Which process? Acha, dq is what? dq is what? You tell me, because you have to answer this always. Will you write dh? Why not? You often say dqs are dh. That is under constant pressure. This is not constant pressure. This is not isothermal pressure. Isothermal condition. This I said a moment ago. Don't jump into dq. dq is dh sometimes. dq is du sometimes. Sometimes neither of them. It is dw, sir. What depends upon irreversibility or reversible. Okay, that's good. Since dq reversible, it must be reversible. So what is this? An ideal gas. So du is out. Du plus dw. This is 0, you know, reversible. You get the answer. Is PdB by T. This must ds is PdB by T. Okay. Or can I? So you can from this. PdB. P by T is what? PdB. PdB. How to get the? Let us see. This is simply in high school problem about say. Okay. This is actually a problem of earlier standard. PdB by T. See, you have to get here. In the exam hall, you are sweating. So this you have started, you don't know this, Maxwell. Oh, big things, sir. This you have done. In your domain, ideal gas, domain. Then how do this? Can anyone tell me? dP is, if I write ds by dB means del S. The moment under constant temperature, it gives you what? Del S by del V at, I'm not writing because I'm not keep it. Del S by del V at constant temperature, isothermal, right? Isothermal condition, okay? Isothermal, right? Good boy and very good boy, okay? Oh dear, right? D is 0 what? Right here, isothermal. Right here, for isothermal process. Why isothermal? So why suddenly isothermal, sir? Can you tell me why isothermal I'm considering? Yes, sir. Use this suitably for isothermal process. Ideal gas is the system. You know very well. So give this. So now tell me. So this brings you del S by del V at constant temperature is what? P by T. So what shall I do? But it's not asked. Del S by del V at constant temperature is P by T. This is not asked. What is asked? Del S by del P. What will write? Does anyone? Del S by means dB comes here as del S del V. No, del S del P. So somehow I have to write del P. Okay. So then again I have to get that del S by del P and del P by del P I have to consider. What is this? PdB is what? What else you know? Quickly, it's okay, it's okay, it's okay. PdB for PdB plus VdP is RdT. PdB plus VdP is RdT forever. Oh no, no restriction. PB is RT, PB is RT is PdB plus VdP is RdT. And for isothermal process is 0. So right is always applied. Your calculus and other things are actually I don't know what type of what has been done previously first year high school. Very difficult. PB is RT, PB is RT. What you can write without any restriction are always right. PdB plus is differentiation plus VdP is what? Tell me. Is now we apply. Now we always do. For ideal gas is a system. So always do. It doesn't apply for gold or lead. Happy to. Now what is PdB now? What I write? PdB is what? Under what we discuss isothermal. So PdB is what? Minus VdP. Here from this. At dt right here 0. Isothermal condition 0. Isothermal will constant. So minus VdP. What is this? What is the answer? Can I double star here? I'm even star here. This is the only place I'm starring. Okay. Can I remove this? Star it, huh? Star. What is hence del S by ds by dp. ds by dp at constant temperature. Remember, the moment you give a constant, write partial derivative. Don't write ds dp. Del S. Partial derivative. Because restriction is there, constant temperature. It is not full derivative. Del S by del P at constant temperature, because under constant temperature we have discussion, is how much? Is minus V by T. Is what? Is also equals to any V by T will answer will do. What are that? So follow. So yes, these two problems are actually challenging problems. Metallurgical students must learn this problem 4 and 5. Okay. What you cannot solve this. Problem 5 you may try. Problem 4, let me. Problem 4. Do you want to try once more tomorrow? You can see this. It is better. You take this. You at least read the problem. At least read the problem and start. Problem 5 we must. You must. I have given this. Okay. Two relation. Del S by del P relation I have given, and del E by del P what I have given. You start the B into B times 1 minus alpha I have given. With this you try to follow. Effect of pressure on enthalpy, effect of temperature on enthalpy. This is very interesting problem. Gaskell. I have written somewhere. I should have written the Gaskell problem. Problem 4 is actually typically metallurgical problem. All metallurgical students all over the world solve this problem. Supercooling of lead or whatever to solid. Okay, supercooling. Why supercooling and how to build this universe? I'm not taking up this because only I will take up and you will write. So 4 and 5 we take up. At least 5 is solved and 4 only read and try. Of course, read at least. So let us move on. Tomorrow is this pending though. So next is what? Next. Okay. So remove. So problem 4 and 5 solved. So problem 4 and 5 will be discussed tomorrow. Will be discussed tomorrow. Tomorrow, so what happens? Tomorrow Friday 10. You are starting 10. Tomorrow. 10 to 12. 10 to 12. Okay. Yes. Come prepare. It's okay. Or do you have a test? City. City? Oh, okay. So this part is over. Okay. Very good. You try. I will help you certainly. Good boy. Acha. So next is third law of thermodynamics. Okay. Next is what? Start. New topic. Next topic. Next topic. The third law of thermodynamics. Let us start. Huh? What is this? The statement. Statement. What is the statement? The entropy of a pure and perfect crystalline solid at 0 degree Kelvin. 0 Kelvin, you know, is 0. Which is in internal, the entropy pure and perfect, which is in internal equilibrium. Which is in internal equilibrium. Internal equilibrium. No, sorry. Which is in, I should write at the end. Which is in at 0 degree Kelvin. At 0 degree Kelvin, right here. Which is in internal equilibrium. Right, okay. Juggle this. Anyway, is 0. That what does it say? S 0 say pure, perfect, pure. 0 of a say species, okay, a metal say. We are metallurgist, metal is 0. At what? Is 0 at what temperature? 298, no, 0 Kelvin. This is the statement of the third law. This will help you find, okay, the for other temperatures. If it is, I use this, so it helps absolute. See, note the absolute value. This is the first time we are coming to this absolute value of entropy. Interesting. We didn't have any such relation, any comparable relation with for enthalpy and internal energy. Internal energy except for ideal gas, enthalpy. But any crystalline solid, 0. Okay. Note the absolute value, no change. Value of the entropy. Okay. It helps to find entropy of M at T Kelvin. How? As you know, what is this relation? You know, start. ds, you know this a moment ago. ds is dq reversible by T, start. I always start to encourage you to actually to give you confidence. ds is dq reversibility is what? Say constant pressure is right here. Okay, you find, okay, constant pressure. So standard state means 1 atmosphere pressure, right? 1 atmosphere pressure. So the N, I'm writing N Cp dt by T under constant pressure. I'm considering this, okay? That means these are same pressure, so 1 atmosphere pressure you may consider. So I'm writing this better, okay? So say I'm writing this here. Sm 0 Kelvin. 0 Kelvin, what pressure? 1 atmospheric pressure. Write this. Is 0 third law. And Sm 0 what Kelvin? T Kelvin. What pressure? 1 atmosphere is what? So I have considered T Kelvin means these both are constant pressure. So Ncp dt by T. What is this? Ncp dt is what? Achha, write this, okay? Or delta S is what? Delta S is what? Tell me. Ncp dt by T integration from 0 to T. Right, actually, dt by T, you can integrate this. Ncp, lnt, etc. So this you can do. What is this delta S? Can you tell me? What is this? St minus S0. State is what? What is the change? This to this. State 1 to state 2. State 1 to state 2. St minus S0, 0 Kelvin. So you can give this, okay, delta S is actually both are standard state. Standard state you may give, okay, so don't worry, I will already mention. St minus S0. What is this? Is what? Right, ditto. What is this value? Third law. Third law. So what is the answer? ST is what? ST was U NC. So this is how you get any temperature absolute. So absolute value at any temperature. Absolute value of S at any temperature. Acha. Okay, over. This is over. Don't worry. I will actually give some comments. I will give you handout. Did I give you handout entropy? I have already. No. I will tell you from gas scale. Okay. Read the handout from the gas scale. Okay. Read the topic from the book of. Read this topic from the book of Dear Gaskell. There are many editions. Okay, don't worry. So what is this now? See, pure perfect crystalline solid. Why solid? 0 degree Kelvin, everything is solid. 0 Kelvin. So everything is below the melting point. 0 degree Kelvin, all have converted into solid. All stuff. All gas, hydrogen, helium, all. Solid. Not only liquid, 0. Solid space. So solid. And pure and perfect, very difficult thing to achieve. Pure and perfect. Pure means pure, no impurity. Perfect solid means, perfect is, there are certain order. Periodic arrangement must be there. Periodic. So periodic arrangement for solid is crystal. Pure perfect, crystal. Crystal is a periodicity. ABC, phase center cubic, stacking A, B, C, as usual, another is HCP. AB. So that's why perfect. So perfect order, perfect actually periodicity. Okay, regular periodicity, and these are, and pure of course purity. So these are. But I show you two cases to discuss. This is given in the note also in the book. 2 cases to discuss. You follow quickly. One is glass. Glass. S of glass into glass. It's a glass. S of this glass at 0 degree Kelvin is 0. Is what? Should be 0. Third law should be 0. The standard state is actually 1. You can read this, okay? 0. Standard state may consider. Write this, no problem. Write or don't write. Is not. Let's say what I'm trying to tell. Glass, glass is a solid thing, solid. But this is not actually crystalline solid. It's amorphous. Amorphous, okay? And it is actually sometimes it is liquid. Supercooled liquid. Glass is not at all solid. Supercooled liquid, viscous liquid, or you may call amorphous, not crystalline. Why this happens? Why it has not solidified? Has formed the crystalline solid? It's because glass is actually has a complex structure. Very complex structure, and as a result of this, having ions, molecules, atoms, like say silicate, and there is actually network formation. Okay, so this big structure, when it is cooled, it is very difficult to bring them into order, into perfect periodicity. Means there are periodic means that's a perfect positions. If that is to be attained, then the atoms should move, ions should move fast enough to take the position. But at 0 Kelvin means when actually the mobility is very small. So it cannot take up. It cannot take up this position, as a result of which this is not perfect crystalline solid. It is not, it is violated. As a result of which it has an entropy. Why, sir? What is that? What I say, since it is liquid actually, what is this? It is still liquid because it has not solid point. Liquid to solid, there should be a freezing point, melting point, freezing point. There is no such thing. Unique freezing point, melting point, and latent heat of enthalpy of freezing, enthalpy of melting. So that is not there. So it is increasing as you decrease the temperature, it becomes liquid, and which is getting more and more viscous liquid or supercooled liquid. And if a liquid, you follow this line, which I'll explain with other properties and other equations, is this that liquid state has a greater entropy than solid. Gas has greater entropy than liquid. Liquid in turn has greater entropy than solid. This I will prove actually soon, and we'll discuss on that. So if it is not solid but liquid, we say actually there is a kind of disorder. Liquid state is more disorder than solid. Solid is crystalline means perfect order. ABC, ABC. Liquid is disorder and gas is the maximum disorder, means there are no fixed position. So liquid. So if you follow that liquid has a greater entropy, then gas is no surprise, which is not solid, crystalline solid, has a some residual entropy which has not fallen to zero in violation of the third law of thermodynamics. This is the discussion. So glass has not zero. You know, glass actually, see, glass is actually, you see, these are typically actually, silicates. Okay, so like say sodium silicate, calcium silicate, borosilicate. This glass actually used in a laboratory. Okay, these beakers, test tube, etc. Okay, other things. Glasswares are borosilicate. And pure glass, if you consider, that is also actually, that is not crystalline. Okay, which is non-crystalline. So idea is glass is an amorphous. It is not a crystalline solid. This first line, not a crystalline solid. This is the reason. This is not a crystalline. What it is? It is a many name amorphous, or sometimes vitreous material. Sometimes we consider it. We may also consider it as a supercooled liquid. We are calling gas solid also. Viscous, supercooled. Supercooled means it's cooled below melting point. Here has no melting point, so it has supercooled or viscous liquid. Since you write this way, since liquid has a greater entropy than corresponding solids, to be shown shortly. So gas, which is liquid actually, viscous liquid, very difficult. Okay, to consider viscous liquid, okay, solid. Okay, non-crystalline. At least say non-crystalline. If glass were crystalline, what would happen? What would happen? I could not wear this one because it is made of glass and light can transmit through this. If it's crystalline, it will opaque, it will not be transparent. So with iron things or lead or say tungsten, gold, you cannot use the spectacles, okay, or any such applications. So fortunate that glass is non-crystalline. Okay. So very good. So you shortly. Then corresponding liquid. So glass will have a residual entropy at 0 Kelvin in violation of the third law. In violation means condition is not violation. It is understood. Why violation? No, condition is given already. Perfect. Solid. It is not crystalline. So why no violation? It is not crystalline solid. So it cannot expect to be zero. And why this has happened? I repeat what I said. It is glass is actually complex. The liquid state complex. Okay, ion or molecules. Okay, silicate. Okay. Complex substance, which has actually, what is this called? Molecules or ions or atoms there. Okay. So silica tetrahedra we speak of. Silica tetrahedra, there is actually bridging oxygen bridge one tetrahedra with another, and this another. It's a long range connection. So big thing. So big when cooling, then to achieve a crystalline solid that is perfect, that's all perfect. arrangement, periodic arrangement. Whole period. Big things very difficult to maintain the periodic arrangement, proper arrangement. Silica must be at the center of a tetrahedral, oxygen at the corners. So coming jumble up. It is not a solid. Because of this, okay? Because this could be, if the mobility would be enough, mobility. So the rearrangement, so reorganization would be fast enough to be crystalline. But at 0 Kelvin, your temperature low means mobility exponentially decreases. Mobility, mobility is, or diffusivity, mobility, all such things. So we don't hope to have a, on this complex structure, complex, glass is a complex structure, okay? Glass is a liquid to solid. You are trying to convert into crystal, solidification, solidifying, trying to solidify. Glass in the liquid state is a complex structure made up of ions or molecules or atoms Okay, so this hence very difficult to achieve a crystalline solid state. To achieve a crystalline solid state at 0 Kelvin. 0 Kelvin is lower the temperature, lower the movement. Almost all stagnant, doesn't try to move, so no need. So at 0 Kelvin, crystal solid state, right here, which requires extensive reorganization, rearrangement of ions, etc. at which requires extension, and it is difficult, hence it is impossible, hence difficult to achieve at 0 degree Kelvin. At 0 Kelvin. Well, these are the other things that you can show. This happens to glass, okay. So good boy. Other things, others maybe lead, solid 0 Kelvin 0. Okay. All these things. Okay. Good boy. Falling down. Okay. This third, another case one, two cases to discuss. Remove this. Two cases to discuss. Next case is very interesting. Case 2. Next, second is vacancy. Presence of vacancy. Presence of vacancy in crystalline, in solids, crystals. Say iron for you. This is what happens here. Vacancy, See, vacancy, I tell you, why vacancy? Suppose this is the structure. Just think, and think. These are the atoms are sitting here. Sitting. Okay, these I am showing, not many, I will draw. These are covered. These are all atoms. Lattice position I mean, okay. So atoms are there. Just I will not. This is another, still another. So metal solid, okay. Since I am draw this, complete this. So this is our atoms and lattice position. What are this right here? This is what? Atoms occupying. Atoms at regular lattice position. Now I tell you what. Consider a metal M. Say iron, say nickel, say. Okay. What happens? This is the solid. Okay, this is the solid. Yeah, atoms are there. At any temperature T, there is vapor pressure. This you have to understand. Solids have at note at any temperature T, solids have their equilibrium. Solids like liquids, Liquids you know, water you know, like liquids have their vapor pressure, own vapor pressure. What will happen? If you try to establish that water evaporates, why? Because in vapor pressure mismatch. So it tries to attain. So it will also try, iron is in the atmosphere. So iron in the atmosphere is not so much, it tries to attain. Okay, maybe, okay, so it's vapor pressure. So the moment tries to escape from the surface, then what will produce? The atom escape. It is a vacant spot. It's called vacancy. So this is vacancy, right? Empty is vacant site. Missing, okay, missing atom, okay, vacant site, okay, missing. Why the evaporator off? It is evaporating off. So going ahead, so some vacancy, I am showing this vacant spot. Suppose this I am showing here. This goes to vapor. I am showing you in the vapor state, gas. Okay, if it goes, then what will happen to this? Tell me what will happen to this? This is empty. This is vacancy. Now what will happen? You know, next is what happened. Vacancy is actually vacancy concentration we speak of. Vacancy here. Let's see another one will do. Another will do. Yeah, here also similarly. Vaporization. What it will be? Again you change this to vacancy. Again another vacancy. Similar many. I have got those number of atoms. I am showing here 5 or 6. Vacancy. Now it tells as follow. If vacancy concentration and the surfaces get, it will try to diffuse downward into the core. So vacancy will be see sometimes this will suppose some vacancy here to come here, then it will go there. Suppose I am showing this is the diffusion of vacancy. So diffusion of vacancy means diffusion of atoms actually. So it like this. This is diffusion of vacancy or atoms. Why this happens? Tell me. Because of obviously concentration gradient. Follow this. High concentration at the top layer, low, so try to come down this. So and this will go up. Then if this happens, this goes up. This goes up. What is the situation? Can I draw once more? This will be here. This will be there. So this next phase. Similarly, see vacancies will be, you get some vacancies. Now about this, there is a nice thing. Now, at any temperature T, there is an equilibrium number of vacancy concentration in a solid. Vacancy concentration in a solid. And concentration means number of vacant site over total site. What is the vacancy concentration? And number of vacant site. Vacancy concentration is what? Number of vacant site. Number of vacant site over total site. Over total sites. This is concentration. That's the equilibrium number. From equilibrium constant, this you will study later. Say 10%. 500 Kelvin, 10%. 10%. If 100 site, 10 will be vacancy. Thermodynamic. This is a thermodynamic. Equilibrium means thermodynamic. Equilibrium means thermodynamic. Thermodynamic means I can give you this actually giving by n total is what? Yeah. N by n total I am giving you is e to the power minus, okay, like this, delta H0 by, okay, delta H by RT or delta G by RT, okay. This type, okay, enthalpy, this is enthalpy activation. Don't worry, this is actually, forget. So there is a certain concentration. What will happen at 0 Kelvin? Third law discussion. At 0 Kelvin, there will be some, there will be even less less and less least. How much? 0. So, and this is vacancy constant. Star, remove this star, and at 0 Kelvin, you may see here perhaps, T is 0. What it is? 0, n by into 10 is the number of vacancy. This is the remove this. This is the number of vacancy and total. Is it? Vacancy constant, n by n total. N is the number of vacant site actually, number of vacancies out of total. T is 0. What is mathematically? If we accept this is actually delta G, my opinion, but I have to think about this. Delta G gives energy. Don't worry. Enthalpy, okay, since our equation, enthalpy consider. Okay. So this is more important. Okay. So T is 0. What is this value? What is the whole value is what? Yeah, yes, right. Minus infinity. E to the minus infinity, 1 by e to the power infinity is 1 by infinity, 0. So 0 concentration. So should not be anything. Free of vacancy. So wait a minute. So and so following the thermodynamic relation. See here thermodynamics. This is physical meteorology. Thermodynamics. Where you will go? Okay. The problem 4. Following the thermodynamic relation. Number of vacancies vacancy concentration should be the number of vacancy by total site. Vacancy concentration should be 0. At 0 Kelvin. 0 Kelvin. 0 Kelvin. Then what will happen? There is no vacancy. So how are vacancies eliminated? What happened? You know, this vacancy. So this exchanging. Follow. This exchanging with this vacancy here. Suppose this exchanging and go to the top, and from the top layer vacancy is out. Top layer vacancy has no meaning. This is eliminated. See all vacancies. This is here. No metal. It is above it. No metal. It's all vacant. So top layer vacancy means they are eliminated from the surface. So 0. That is, all vacancies should go to the surface. Where they are eliminated. See argument follow the argument. Must some vacancy must. Later on you study about this. Some during casting also solidification some vacancies are generated. But thermodynamics says given no defect, no nothing, thermodynamically there will be some vacancy. Because some will be evaporate off. This is vapor, this is evaporation, right? Evaporation. And vacancy created. Everything from the surface, and vacancy created. There's a little bit vacancy created. Short. So give that this. So vacancy created, vacancy then enter into this at a given temperature. Now you are gradually reducing the temperature. It's difficult to come by. Impossible. So some fine temperature, there are vacancies. They are produced or evaporated there, and then they are migrating from say the distribution. 10% vacancy. But you want to reach to 0 Kelvin. 0 Kelvin, what should suppose some vacancy are here. Some vacancy here. At a given temperature. Now you are reducing the temperature 0 Kelvin. What they should do? Consistent with this to be going top. Vacancy will be 0. So where they are eliminated? How they are eliminated? So these exchanges vacancy here. This exchange vacancy here. This exchange vacancy here. And then on the top surface they are eliminated. I have written that. Vacancy should reach the surface, go to the surface, should reach the surface, go to the surface and or diffuse to the surface, should diffuse to the surface where they are eliminated. Surface at the surface means gone. This means surface, you see surface, then there is no more vacancy. Okay? So So see, top layer vacancies, full of vacancies, means one layer down. All vacancies, one layer down. So that is actually the surface is eliminated. Now tell me, it is possible all vacancies should go there and will be eliminated? This requires movement, diffusion, and diffusion is very slow at 0 Kelvin. So what will happen? You will not be able to. So it should go there, but there is no mobility. There is no diffusion. There is no mobility, and it will lock there, arrested there. So some vacancy will be there. This is called actually at 0 Kelvin there is some vacancies, and if there are some vacancies, actually this is the latest part. Suppose some vacancies, say 5 vacancies are locked at 0 Kelvin. They can sit here, they can sit here, sit here, sit here. This type of reorganization, okay, this will bring in some entropy. Increase of this system. This can be discussed why when you actually there are rearrangement of their vacancy. So this is called actually may see number of vacancy here. So number of possible configurations are there. So entropy will be created. Otherwise entropy would be okay 0. So this I will discuss actually what is called this configuration entropy change. Okay, this actually one configuration, another configuration, still another. So what is this? They are eliminated. But at 0 Kelvin, diffusion is slow. And some vacancies are arrested, locked, are arrested within the crystal, within the solid. And these vacancies and this arrangement, vacancy where, here, these possibilities is entropy. This I will say configuration entropy. And I am not writing here, and causing entropy, causing an increase in entropy. Causing it because, this causes, remove this, based on the possible rearrangement, possible arrangement of the vacancies of this possible arrangement of these vacancies within the crystal, arrangement of these vacancies within the crystal, the solid will acquire some, what is this called? Entropy. This is called configurational. Configuration means here or there arrangement. Arrangement is configuration. Some configurational entropy. So entropy is not reduced to 0. Thus, so entropy at 0 Kelvin, I have written somewhere here 0 Kelvin. So entropy of the solid, crystalline. This is not about crystalline or non-crystalline, not glass. Crystalline very much, but it's a lead, it's a gold. So entropy of the crystalline of the crystalline solid does not fall to 0 at 0 Kelvin. These are two actual typical discussion. There may be other situations. This is about third law. Okay? Achha, how much time I get? Maybe 2, 3, 5 minutes will 10 minutes. 10 minutes I shall get. 10 minutes okay to? Then I will cover. Follow. Why? Next, entropy entropy, disorder, and probability. Quickly, this will conclude discussion of entropy, including the third law. Okay. Actually, I could not. I have to discuss two problems, so that I thought I use this. See, follow this. Consider this. Consider S M. Consider metal M. And we are trying to find entropy S of M at T Kelvin, where T is greater than boiling point, and boiling point is always greater than melting point. TBM, TMM. At a temperature T which exceeds boiling point, and boiling point of course exceeds melting point. So boiling point, this is melting point. Quickly, you will understand why liquids have greater entropy. I said no? I'll explain this. So if you start SMT Kelvin, I start with what? Say 0. Third law is there. Remember, a moment ago I gave you the relation between two temperatures, SMT and SM0. Okay, remember this. What is that I wrote? SM 0 Kelvin plus what happens? Tell me. Cp what? At 0 Kelvin, what it is? What state it is? What state? The any metal? What state? Solid. Cp M solid dt. Happy? What is what? Tell me. What temperature? 0 to what temperature? Up to which temperature go? Solid, if is solid to up to the melting point. 0 to Tm. Solid domain. Then what will happen? Tell me. Then what will happen? Melting will happen. Enthalpy of melting, you know, this is entropy of melting. What is this? Sir, enthalpy of melting divided by the melting point. You know, dq. Okay, is actually Q dq reversible or reversible melting point under constant pressure. Okay, at constant, right? Consider pressure is constant. So effect of temperature I am showing. So delta H in enthalpy of melting by dq reversible. Dq is dH under constant pressure. dH is delta H and T is the melting point. The phase transformation. Yeah, phase transformation, right? Phase enthalpy of melting. As you know already, you know. This is called phase transformation. Phase means solid to liquid. Happy? Then what will happen? Liquid. Next, the solid has been liquid. So next will happen again further heating to T. T is the target. Then what will happen? You know this. I did this once. Then what will happen? Cp M what? It was solid dt. This part remember dt Cp dt I showed you a moment ago. dq ds is dqt Cpt integration, and this is Cpm. Tell me what heat has been already by this process liquid. So hot temperature. Tell me which temperature? Tm to what? Boiling point. Follow this dt by T. Oh sorry, here sorry. This is hot mistake I made. ds is dq reversible Cp dt by T. Okay. Enthalpy is Cp dt. It is Cp dt by T. Cp dt by T. Three things. Can I remove this further? Then next what will happen goes to boiling point. Then you may consider evaporation or vaporization. Can I remove this? Get a space here. Delta H vaporization by boiling point. Same entropy. This is enthalpy, this is entropy by temperature. Okay. dq reversible by T we apply. Good. Next what it will happen? Next T is not yet reached. Boiling point is reached. Then it moves to Cp. M has been what? What? It has been now. After vapor, it is no longer liquid. Vapor by T. Tb to T. So follow this. Then you will have a feelings. New thing. So tell me. Okay, happy to. So entropy increasing. What is the domain of the solid? How long it is solid? These two terms. These two terms. Domain of solid. Domain of solid. Solid M. What is the domain of liquid M? Tell me. I am showing you. Again, starting from here, covering a liquid will have how much entropy? Okay. This is liquid. It is not yet vapor. So this is the domain of the liquid entropy. From starting from, so domain, anytime you have domain of entropy domain. Entropy domain, better term. Entropy domain of liquid M. So if you want to get the liquid entropy, how will you get it? Starting from the same value, you go through and get more and more and more. What is the entropy domain of vapor M? Entropy domain of vapor M. Vapor means gas, right? Gas. Vapor is gas. What is the conclusion? Which is greater? Which is greater here? Greatest. Vapor. Basic, this has the entropy this much. Liquid, this much. Solid, this much. So what is conclusion? So conclusion, S of solid, gas, you write. Gas is greater than S of liquid. S I am discussing, not delta S. S, direct, greater than S of what it is? Solid. And also remember, and also note, if I ask you disorder, order, disorder, structure, liquid, solid, gas, which is the most disorder? Yes. Because you know there is no any position here, molecules randomly moving. And liquid is next, liquid has actually some order, but it is some only, okay? Limited order, okay? Short range order maybe, but then it is again random. And solid, this solid has crystalline periodicity and order. So also the degree of disorder, okay, disorder increases as what? Which is a, who increases disorder? Which has gas greater than disorder, liquid, least is solid. Solid is order. So what is the meaning? That looks like same trend. So entropy is a measure of disorder. We can conclude. So we can conclude entropy that entropy is a measure of disorder. Is a measure of disorder of the system. Disorder time, how many 5 minutes? 10 minutes. Entropy is a measure of the disorder of the system. Okay. Huh? 5 minutes. Okay. Entropy is a measure of disorder of the system. So this is one. That gives use the term. So this is a common phrase. Entropy is a measure of disorder. Follow this. And practically follow this. This is practical. We will discuss a little bit of statistical today, but this today means next class. But today gives he doesn't use the disorder. He gives used the term mixed upness. And next day I will actually mixed upness. So he says, and according to him, entropy is a measure of mixed upness. This I will discuss. This I will clarify next class. Early, okay, couple of minutes on this. Then you will go over measure of mixed terminus. This I don't want to talk on this. Here, measure of mixed terminus of the system. This I will show you. A little bit of quantum theory comes small though, but this discuss. Okay. Thank you. With these words, we have completed today's class. Okay. We'll meet tomorrow. Okay, for subsequent discussion, and we'll introduce this finality next class. Thank you. Oh, very good. So wait a bit. Thank you so much. So please, I have made a mistake here. Please follow that this is not 30. This is a 2-period class. So it has been 2 periods. So it will be. It is not 38. It is 38. Please note this. It is 38, 39. It is today 2 periods. Thank you very much.